Let's finish the modern physics in next 15 to 20 minutes. My dear NEET aspirants, I'm not going to leave any of the topics out there. Trust me, this is going to be very helpful. And if you want to leave any of the chapters out there, but do not leave modern physics, okay? So let's dive into the complete modern physics in next 15 to 20 minutes. First topic that we need to understand over here, that is energy of a photon. We say energy of a photon is h into f. H means Planck's constant, f means frequency. F we further say c divided by lambda. C is speed of light, lambda is wavelength. So we can say energy is equal to hc divided by lambda. So value of Planck's constant is 6.6 into 10 raised power minus 34. Value of c is 3 into 10 raised power 8. And if you put the values of h and c over here, you will finally get energy of photon 2 into 10 raised power minus 25. That is divided by lambda. This lambda is in meters, energy is in joules. Okay. Then further, my dear NEET aspirants, we further say energy of a photon is also equal to this. That is 12400 and divided by lambda. But here we take lambda in angstrom and energy in electron volts. And we also say energy of a photon is 12400 in electron volts, but lambda is in nanometers. So use this when lambda is given in angstrom. Use this when lambda is given in nanometers. Like my dear NEET aspirants, if I say photon has got a wavelength of 4000 angstrom, in this particular case, we'll be using this to find the energy. If energy of a photon is then, if wavelength is in nanometer, we'll be using this to find the energy of a photon in this particular case. Let's dive into the next one. Now, when it comes to the energy of light, my dear NEET aspirant, energy of light is simply, that means NHF. Energy of light means energy of n number of photons, large number of photons. So you can further write it NHC divided by lambda, because F is also C divided by lambda. Then, my dear NEET aspirants, momentum of a photon. We say momentum of a photon is H divided by lambda, where H is Planck's constant and lambda is de Broglie's wavelength. Okay, this is also one more relation that I want you guys to remember. This is the relation between energy and momentum of a photon. E is equal to P into C. Okay, this relation also I want you to remember. This is what we call the moving mass of a photon, because we say rest mass of a photon is 0. H divided by lambda c. Then, my dear NEET aspirants, we define power of light. Power of light is simply energy divided by time. How much energy is falling? Like this bulb is sending more energy, more photons every second. So power of this is large as compared to this. So power is energy upon time. Energy we write NHF divided by T. You can also write NHC divided by lambda into T. So from here you can also calculate number of photons per second also. Then, my dear NEET aspirants, intensity of light. Intensity is simply defined as energy upon time into area. So we can also say power divided by area. This is the formula NHF divided by A into C. This is what we call the intensity of light. Then, my dear NEET aspirants, we say in case of a point source, if you have a point source, we say intensity at R distance will be power divided by 4 pi R square. Okay. In case of a line source, means a tube light, intensity at R distance will be power divided by 2 pi R into L. Then, my dear NEET aspirants, we say radiation pressure. If light or radiation falls on the surface, it creates pressure on the surface. And if it is completely absorbing surface, we say pressure is I divided by C. Okay. You can also write this force acting on the surface is I into A divided by C, where I is intensity, A is area, and C is speed of light. If it is a completely reflecting surface, in that case, we say this pressure is 2I divided by C, and force will be 2IA divided by C, where I is intensity, C is speed of light. This is for completely reflecting surface. Now, my dear NEET aspirants, we have photoelectric effect. Photoelectric effect is when photons fall on the metal surface, light fall on the metal surface, electrons are ejected from the metal surface. This phenomena is called photoelectric effect. Okay. And then, my dear NEET aspirants, we say experimental setup of photoelectric effect. When electrons fall on the metal surface, electrons are ejected from the metal surface. So, my dear NEET aspirants, we say when photon falls on the metal surface, the energy of a photon is used in work function. Work function is the minimum amount of energy required to pull the electrons from the metal surface. So basically, when photon falls on the metal surface, it gives the energy to the electron, and that electron uses that energy in order to come out of the metal surface and so that it moves further forward. So we say work function plus kinetic energy maximum. This is what we call Einstein's photoelectric equation. And my dear NEET aspirants, we also say kinetic energy of electron is EV0, where V0 is the stopping potential. You guys need to remember this also. And my dear NEET aspirants, when photons fall on the metal surface on this cathode, electrons come out of this cathode and they start moving. When they start moving, they create photocurrent. And then, my dear NEET aspirants, if we make the graph between photocurrent and EMF, so it is something like this. It is something like this. And this potential where photocurrent is 0, this is what we call the stopping potential. And at stopping potential, kinetic energy of the electron is EV0. I can say it something like this. Then, my dear NEET aspirants, one more important thing. We say frequency is directly proportional to photon energy. Photon energy is directly proportional to kinetic energy of electron, which is directly proportional to the stopping potential. Similarly, intensity is directly proportional to the number of photons, which is directly proportional to the number of electrons, which is directly proportional to the photocurrent. Then, my dear NEET aspirants, one thing I want you to remember over here, stopping potential has a relation with frequency. Photocurrent has a relation with intensity. If you take a look at these three graphs over here, they have got same current. This is photocurrent. Okay, same photocurrent. If photocurrent is same, means intensity of the three graphs is same. And if stopping potential is different, so means frequency of the three is different, because frequency has the relation with stopping potential. Here in this case, we say stopping potential of two graphs is same, so frequency is same. And in this case, we say photocurrent is different, so my dear NEET aspirants, intensity is different. So intensity of this is greater than intensity of this. Then these are the different versions of Einstein's photoelectric equation. You can write it like this also. Phi plus kinetic energy maximum. Phi, energy of photon is h into f. This you can write h into f naught, where f naught is threshold frequency, minimum frequency required to pull the electron from the metal surface. ev naught, you can write it like this. You can write f is equal to c divided by lambda also. hc divided by lambda is equal to hc divided by lambda naught. This is threshold wavelength plus ev naught. You can write it like this also. Energy of photon is h into f, and work function is h into f naught plus 1 by 2 mv square. And my dear NEET aspirants, h, you can write it like this also. hc by lambda is equal to hc by lambda naught plus 1 by 2 mv square. Then my dear NEET aspirants, de Broglie's wavelength, matter wavelength. De Broglie said everything in this universe is a particle as well as it is a wave. Like this pen, it is a particle as well as this is wave. And what is the wavelength of this particle? You can say h divided by mv or h divided by p, where mv is the momentum, my dear NEET aspirants. Now we say de Broglie's wavelength in terms of kinetic energy. De Broglie's wavelength in terms of kinetic energy over here. Okay, so we say in terms of kinetic energy, this is de Broglie's wavelength in terms of momentum, in terms of kinetic energy, which is h upon under root of 2 mke. Then de Broglie's wavelength for a charged particle accelerated under potential difference delta v. So that is lambda is equal to h upon under root of 2 mq delta v. H is Planck's constant, m is mass, q is charge, delta v is the potential difference. Then my dear NEET aspirants, we said de Broglie's wavelength for a relativistic particle. Relativistic particle is that particle which is having the speed, approximately speed of like electron, proton, which moves with a very faster speed. Okay, its de Broglie's wavelength is this much. Okay, h 1 minus v square by c square. V is the speed of that particle, c is the speed of light. M naught is the rest mass of that particle, v is the speed of that particle, and h is Planck's constant. De Broglie's wavelength for a charged particle at rest placed in electric field. So it has de Broglie's wavelength h divided by q e t. Q is charge, e is electric field, t is time. Then my dear NEET aspirants, de Broglie's wavelength for a charged particle placed in the magnetic field. If a charged particle is placed in magnetic field, its de Broglie's wavelength is h upon q b r. Q is charge, b is magnetic field, r is the radius, because here particle moves in a circular path when it goes into the magnetic field perpendicularly. For a gaseous molecule, it is h upon under root of 3 mkbt, where kb is the Boltzmann's constant and t is temperature. For an electron moving in the nth orbit of an electron, so we say its de Broglie's wavelength is n into h upon under root of 2m into 13.6. Then my dear NEET aspirants, we are done with the dual nature and matter and radiations. Now we have atomic physics. First model of atom was Thomson's atomic model. Thomson said that an atom is exactly like watermelon, in which this red portion which we eat, it means positive charge, and the seeds, okay, these seeds represent electrons. Okay, seeds represent electrons. And he also said atom is electrically neutral, means number of positive charge, the amount of positive charge in an atom is equal to the amount of negative charge. Okay, so this was basically Thomson's model. Then my dear NEET aspirants, came the Rutherford's atomic model. Rutherford's atomic model, he performed an experiment, that is what we call alpha particle scattering experiment. And in that alpha particle scattering experiment, he took alpha source from which the alpha particles were coming out, and it were crossing the gold foil. And he observed 99.86% alpha particles were directly crossing on the screen, directly crossing the gold foil and were falling on the screen. And only 0.14% were deviating. That means 1 in 8,000 alpha particles are deviated. What does it mean? What does it mean? It means if all the alpha particle means positive charge, if all the alpha particles are crossing, so means positive charge is not present in the entire sphere. If the positive charge is present in the entire sphere, then it would have repelled these alpha particles. Okay, so he said positive charge is present at a unique place. That is what we call the nucleus. That is what we call nucleus. And electrons are revolving around the nucleus in random orbits, not in a fixed orbit. So this was Rutherford's atomic model. Then we said distance of closest approach. My dear NEET aspirants, this is an alpha particle which is having the positive charge 2e. If you throw this with an velocity v alpha, so here you place an atom which is having the atomic number z. This is the charge on atom. All right, people. Now, my dear NEET aspirants, when you throw this, so this positive charged atom or positive charged nucleus, it is going to repel this positive charge. So it will come close. At certain distance, it will face maximum repulsion and it will be repelled back. This distance is what we call the distance of closest approach. And this distance of closest approach in terms of kinetic energy is K, Q1, Q2. Okay, so Q1, Q2 divided by kinetic energy. And R minimum in terms of atomic number, you can write it over here, Z E square upon pi epsilon naught, mass of alpha particle into velocity of alpha particle square. This is distance of closest approach. Then, my dear NEET aspirants, Bohr's atomic model. Bohr's first postulate says that an electron which is revolving in an orbit means it is accelerating in an orbit. So whenever electron accelerates in an orbit, it produces wave. He said it produces the stationary wave. And stationary wave does not radiate the energy, it does not lose the energy. Hence, an electron revolving in the around the nucleus does not lose energy. So if it does not lose energy, so electron will not collapse into the nucleus. Hence, we say atom is stable. He defined the stability of an atom. Then, my dear NEET aspirants, Bohr's second postulate. According to the second postulate, my dear NEET aspirants, we say an electron revolves around only in those orbits where its angular momentum is nh by 2 pi. So Bohr's second postulate says electron can only revolve in those orbits where its angular momentum is 2 pi, not like Rutherford. Rutherford said it revolves in the random orbits. Okay, n can be 1. If n is 1, the angular momentum will be h by 2 pi. If n is 3, it will be 3h by, I would say. If n is 2, it will be nh by, that is 2h by 2 pi. Okay, then, my dear NEET aspirants, Bohr's third postulate says that if electron revolves in the higher orbit and makes the transition to the lower orbit, energy is released in the form of photon. If electron is revolving in the lower orbit, makes the transition to the higher orbit, we say energy is absorbed in that particular case. Then mathematical analysis, velocity of an electron in the nth orbit. This, if an electron is revolving in the nth orbit, this is the nucleus having charge Z, its velocity will be E square 2 epsilon naught h is Planck's constant, Z by n. Z is the atomic number. And my dear NEET aspirants, you can write it like this also, 2.2 into 10 raised power 6 Z by n, or V naught Z by n. Okay, these are the two graphs, okay, V versus N, V versus Z. Then radius of an electron in the nth orbit, my dear NEET aspirants. So we say if this is Z and this is the radius R, this electron is revolving in the nth orbit. So this will be the radius R naught n square by Z. This is the value of R naught, or R naught is 0.53 angstrom also. Okay, these are the three graphs which I would like you to understand over here between, you can see it from your end only. Then the time period of an electron, how much time an electron takes in completing one cycle, that is T naught n cube divided by Z square, value of T naught is this. Then my dear NEET aspirants, we say, and n in this particular case means which orbit? Nth orbit. If I'm talking about second orbit means n is 2. Frequency of an electron in the nth orbit. So frequency of an electron in the nth orbit is 2 by 3, 10 raised power 16 Z square by n cube. By magnetic field, when an electron revolves around the nucleus, it produces magnetic field at the center. How much magnetic field at the center? B naught Z cube by n raised power 5. This is the value of B naught. Then my dear NEET aspirants, total energy of an electron in the nth orbit. If an electron revolves in the nth orbit, okay, its kinetic energy will be, because it has mass, it has velocity, its kinetic energy will be Z e square 8 pi epsilon naught r. Its potential energy will be minus Z e square upon 4 pi epsilon naught r. So total energy will be, total energy is kinetic energy plus potential energy. So if you add these two, it will come out to be minus Z e square upon 8 pi epsilon naught r. Okay, you can also write total energy is negative of kinetic energy. See, total energy and kinetic energy is exactly equal, but this is negative. Or total energy is mod of this is mod of this. Kinetic energy is 1/2 of this much, that is kinetic energy is potential energy divided by 2. You can remember these expressions also. Okay, graph between energy versus R. So kinetic energy is since positive, so graph will be from upper side. Total energy is negative and potential energy is negative. Graph will be from lower side. This is potential and this is total. Then my dear NEET aspirants, if we talk about hydrogen atom, this is one more equation for total energy of an electron. So we say total energy of an electron is also equal to, okay, minus 13.6, okay, Z square divided by N square. For hydrogen atom, we say Z is equal to, my dear friends, 1. So the 13.6 divided by N square. So this is the energy of an electron in the first orbit in hydrogen atom, minus 13.6. In second orbit, minus 3.4. In third orbit, minus 1.5. And you can see it exactly over here. Then my dear NEET aspirant, spectrum. When a white light is passed through the prism, it is split into 7 different colors, V, I, P, G, Y, O, R. And then if you place a screen over here, photographic plate over here, and on the screen we say these different spots will be created, red, blue, violet, indigo. This creation of these spots is what we call the spectrum on the screen. Okay, this creation of spots of different wavelengths is called a spectrum. Now my dear NEET aspirants, you have absorption spectrum. When an electron, listen to me very carefully, is revolving in this orbit, and energy is 13.6, in the second orbit minus 3.4. So this gap is 10.2 electron volts. If you subtract this from this is 10.2. If you send a photon of 10.2 electron volts, it is going to absorb that and make the transition to the higher orbit. When it makes the transition to the higher orbit, on the screen a dark spot is created. So on the bright screen dark spot is created. This is called absorption spectrum, because absorption spectrum means a photon has been eaten up by the electron. That's why dark spot was created. And when an electron makes the transition from higher orbit to lower orbit, photon is released and which falls onto the spectrum on the screen. So bright spot is created. This is called emission spectrum. Okay, then my dear NEET aspirants, this spectrum creation when electron moves from higher orbit to the lower orbit, this we show in the spectral series also. In spectral series, first is Lyman series, we show it when electron makes the transition from higher orbit to the first orbit, okay, like from second to first, from third to first, fourth to fifth, first, okay, fifth to first, okay. So this we show in the Lyman series. So in Lyman series we show if electron moves finally to first orbit, initially from second, third, fourth, okay. So for first line energy is minimum, frequency is minimum, lambda is maximum. For last line energy is maximum, we say frequency is maximum, this is minimum. And similarly in Balmer series we show if electron moves from higher orbit to the second orbit, okay, like this. Here final orbit in this case is 2, initial can be 3, 4, 5 and so on. And in Paschen series we say electron finally moves to the third orbit, okay, final is third. And in bracket series, finally electron moves to the fourth orbit, okay. And in Pfund series, finally electron moves to the fifth orbit. Now, if somebody says this line, how much wavelength this line actually has, this is the wavelength of the line when electron moves from higher orbit to the lower orbit. 1 by lambda r, 1 by n final square minus 1 by n initial square. R is what we call the Rydberg constant. N final is the final orbit in which it is landing, and initial is the initial orbit in which it is landing. Okay. Now, if an electron makes the transition from higher orbit to the lower orbit, like from third to first, it can directly come from third to first. It can come from third to second, from second to first. How many lines are created? 3. How many spectral lines are created? This is the formula. N2 minus N1 into N2 minus N1 plus 1 divided by 2. This is how we can find the number of spectral lines formed. Okay. Then my dear NEET aspirants, we have nuclei. When it comes to the chapter nuclei, so nuclei means, nucleus means which is at the center of the atom. So inside the nucleus you have protons plus neutrons. These are what we call the nucleons. The particles which lie inside the nucleus are called nucleons. And representation of a nucleus is something like this. We say this is a letter and this is A, this is Z. A means mass number of protons plus number of neutrons. Z means atomic number of protons. A minus Z means number of neutrons. Like this has mass number 10, atomic number 5, so number of neutrons. neutrons is also 5 in this case. Okay, rest mass energy. If there is a mass, okay, due to the mass of an object, energy is associated with it. That is what we call rest mass energy. And rest mass energy, we say E is equal to mc square. If let's suppose mass is 10, c is speed of light, so energy in 10 kg is 9 into 10 raised power 17 joules. This is what we call the rest mass energy. And size of nucleus, or we say nuclear size. So when we talk about the nuclear size, that means the radius of nucleus. We can write it like this. Radius of nucleus is r naught, a raised power 1 by 3. A means the mass number. R naught is basically the constant over here. Or we say volume of nucleus is V naught into A. Okay, nuclear density of nucleus. We say density of nucleus is simply 10 raised power 17 kg per meter cube. It is same for all the nuclei. Okay, it is same for all the nuclei. It does not depend upon the mass number. Then we say binding energy and mass defect. My dear NEET aspirants, if this is a nucleus, okay, if it has mass number A, atomic number Z, A minus Z is the number of neutrons. Let's suppose its mass is M. If you break this nucleus in this particular case, okay, so means you use some energy in breaking the nucleus. And you took all the nuclear, these protons out. How many protons? Z means number of protons. So Z, mass of proton is MP. Z MP is the number of protons. And this is the mass of Z protons. And A minus Z is the neutrons. So mass of neutron is Mn. A minus Z is the mass of neutrons. Now, we saw that this mass came out to be greater than the collective mass. When they were inside, they were having less mass. When they were outside, they were having more mass. So we say mass defect has occurred. How to find that mass defect? Mass defect means this mass, final mass, Z MP plus A minus Z Mn minus initial mass. And this mass defect is because when you broke the nucleus, the energy which is used in breaking the nucleus is stored in the form of mass of the nucleons. That's why mass defect occurred. So this energy which is used to break the nucleus is what we call the binding energy. Due to this binding energy, only mass defect occurs. So binding energy is delta M into C square. And this is the mass defect into, I would say, C square. You can see it over here. Then, my dear NEET aspirants, we say binding energy per nucleon, it is proportional to stability. Okay, binding energy per nucleon means the amount of binding energy used so that you can take out one nucleon from the nucleus. So that is what we call the binding energy per nucleon. Okay, graph between binding energy or stability versus mass number. See, this is the graph. Now, here we say mass number is 30, here we say mass number is 70. Those nuclei which has got mass number less than 30, those are what we call the unstable nuclei. Those nuclei with mass number less than, okay, mass number less than 30, those are called unstable nuclei. Now this and this is unstable, so they will basically fuse together. So between the nuclei A is equal to 30 to 170, these are stable nuclei. They will fuse together to form a bigger nuclei. Okay, so like 15 plus 16, this is 31 mass number, so this is stable. So this process in which two nuclei fuse together to reach stability, this is what we call fusion. So when a bigger nuclei breaks into smaller nuclei to attain stability, this is called fission. Because see, all of these have less binding energy per nucleon stability. This also has less, so this portion has got higher stability. That's why fission and fusion takes place. Okay. Yes, Q value of the reaction. We say when, my dear NEET aspirants, reactant nuclei are converted into product nuclei. In that particular case, some energy is released or absorbed. This energy is what we call, this energy released or absorbed is what we call the Q value of the reaction. And my dear NEET aspirants, when you talk about the Q value of the reaction, listen to me very carefully. You say it is, this Q value of the reaction will be mass of reactants minus mass of products into C square. So you can write it like this. This is reactants minus mass of products into C square. In terms of binding energy, we write it like this. Binding energy of products minus binding energy of reactants. So binding energy of C plus binding energy of D minus binding energy of A plus binding energy of B. So this will be Q value of the reaction. Okay. Yes. Now, alpha, beta plus decay, beta minus decay, alpha decay. We make a graph between number of protons plus number of neutrons. This curve is what we call stability curve. This nuclei has got large number of neutrons. It is also unstable. This has got large number of protons. It is also unstable. This has got both large protons, large neutrons. This is also unstable. So basically, this nucleus will try to reach the stability curve. It will lose one neutron. It will gain one proton. Okay. Then again, one neutron gains one proton. It reaches stability curve. This process, losing one neutron or converting one neutron into one proton, this is called beta minus decay, my dear NEET aspirants. Okay. And here, this has got large number of protons. So it will lose one proton, gain one neutron. Lose one proton, gain one neutron, and reach a stability curve. This is what we call losing one proton and gaining one neutron. This is called beta plus decay. And this. We say in this particular case, it will lose two neutrons because it has got large neutrons, large protons, and it will lose two protons. Again, two neutrons, two protons. So this is what we call, this is what we call alpha decay. So my dear NEET aspirants, see beta decay. When a nucleus, this is nucleus Z, it is having mass number A, Z is the atomic number. Basically, it loses. So this is basically in terms of beta minus decay, we say an electron is coming out. Okay, so we say an electron is coming out. That's why we call it the beta minus decay. In terms of beta, in case of beta minus decay, we say mass number remains the same. So atomic number increases by 1. You can understand it like this. And when it comes to the beta plus decay, so we say mass number remains the same and atomic number decreases by 1. You can keep it like this. Okay. And in case of alpha decay, my dear NEET aspirants, C nucleus will do the alpha decay. We say in this particular case, mass number decreases by 4 because it is losing four particles in total, 2 neutrons, 2 protons. So mass number decreases by 2 and atomic number decreases by 2, mass number decreases by 4, and an alpha particle is coming out. That's why we call it alpha decay. So that's all for this, my dear NEET aspirants. Okay. One more important thing over here. We say recoil velocity of the daughter nucleus. So we say in this particular case, we say when alpha decay takes place, when alpha particle comes out. So what is the velocity of the daughter nucleus? Recoil velocity. This is mass of alpha, velocity of alpha divided by mass of the daughter nucleus. You can keep it like this. Okay. That's all for today. Thank you so much, guys. Take care and bye.